Welcome, everyone. Thanks for having me over here, Peter and QCon. This talk might have the sort of peculiar title, From Microliths to Microsystems, but I'll try to explain what I mean throughout. In essence, it's a talk about microservices, but from an architectural and especially distributed systems perspective. So let's get right into it. We've been spoiled by the once believed almighty monolith, Hail monolith, right? With this single SQL database and one thread being spawned per request, and sort of this strong coupling, and that sort of has given us sort of an environment where we could assume one single now, essentially, that we are like full control of time, and there's just one present. And you can make a lot of assumptions and simplify the world quite a lot by being allowed to have such assumptions. But the problem is that it's really a fictional or a fairy tale world, really, and we're sort of living in this illusion that this is real life, but it's not really. And it's sort of a world where we could, at least we think that we could sort of comfortably forget about the university classes and distributed systems that we learned 10, 20 years ago. Well, knock, knock. Who's there? Reality. We have been living in an illusion, quite often quite far from reality, actually. It's just to look around and see. I mean, the systems that we have built in this monolithic, simplified world doesn't really match any of this anyway, I mean, how the world actually works. And I'll explain what I mean by that throughout this talk. You know, today, most applications are deployed on everything from mobile devices to often running multi-core, often quad-core processors nowadays, but all the way up to these huge cloud environments running thousands of nodes, often 8 and 16 core machines, and where users sort of expects millisecond response times. Users are extremely picky and demanding nowadays, and reliability has to be close to 100%. It's of course not physically possible, but we need to get quite far there. If the system's down for too long, I mean, users will go to a competitor and you will lose business in the end. And so it's a fact that traditional architectures and the way we build software up till this point, or at least up to the point by 5, 7, in some cases 10 years ago, simply does not cut it anymore. We need new tools and new ways of thinking, new ways to model the world in software. In essence, we can't make the horse faster any longer. I mean, we need cars for where we're going. So it's really time for us to wake up, time to retire this monolith, and so start decomposing the system sort of into discrete services that can be scaled individually, that can fail individually, that can be replicated individually. As also that can gives us tools to scale the organization, which is a lot what microservices is all about. It's not just an architectural pattern, it's actually a way to meet time to market with a large organization. So these services have had many names over the years. We've sort of done full circle once again as an industry. If you've been around for more than 10 years, you see the signs. We're back to square one again. But I think we're getting a little bit better each time around, so to speak. But I also think it's important, even though microservices is extremely hot, to not just drink the Kool-Aid. Microservices come with the cost, and you need to sit down and look at what you actually want to achieve and see, is it worth to pay that price? Very often it is, but sometimes it isn't. It depends on team size and reliability guarantees and et cetera, et cetera. And it's actually a fact that no one really wants microservices. It is just as concurrency, just as distributed systems, just as eventual consistency, et cetera. It's a necessary evil. It's a means to an end, not just something that we should just apply to everything because it's cool and because we read about it on InfoQ. But today we're going to take a look at microservices and not from the sort of scaling the organization perspective, but from an architectural perspective, and put it in its true context, distributed systems. Okay? So let's say we want to slice that. We have a monolith now, and we want to slice that up into individual discrete services for scaling, for reliability, etc. I mean, it might be a classic JE application, servlets, EJBs, I mean, using Oracle as a SQL database, or whatever, deployed in WebLogic server or something like that. So very often, too often, I'd say, we end up with something like this. We have single instance services that are communicating over synchronous HTTP, sometimes over REST, most often over REST. Each one run in a Docker container, spin it up in the cloud, etc. With using regular CRUD, create, read, update, delete, talking through JPA down into sort of often one single database with discrete schemas, which might be okay. Absolutely, if you know that you can't cheat and call into each other's sort of view of the world. But this is often when I'm out there seen as sort of state of the art. Okay, the problem is that what we've done is that we built ourselves a set of single instance micro monoliths. That's what I call microliths, where sort of state and behavior is still coupled, and we have synchronous execution across throughout, calling down to the database, and synchronous communication across these services. Essentially taking every method dispatch and just making it into a REST call. I mean, you might be able to scale the organization through well-defined protocols, but you won't be able to reap any of the benefits from an architectural standpoint that microservices actually can give us, and that's what I want to talk about. I call them macroliths for a lot of reasons. One of them is that they have extremely sharp edges, right? You should expect to get hurt if you start playing with these things. And by definition, they are not elastic because the single instance can't scale, and they are not resilient because the single instance can't sort of self-heal. I mean, sure it can come back online, but you will lose business during the downtime. Okay? So just relying on a single instance just won't cut it. So in the spirit of Carl Hewitt once said that one actor is no actor, actors come in system. I say one microservice is no microservice. Microservice, they come in systems. Okay? Just like we humans, I mean, we work best when even though all of us are autonomous, we think in an autonomous fashion, we act independently, etc., of each other, but we need to communicate and collaborate with others to solve problems, and it's in this communication and when we help each other out that we can really solve hard problems. It's also actually in the communication etc. that's most of the problems arise, right? I mean, sort of through not understanding each other, etc. And I think that also, all this sort of matches very, very well into microservices architectures as well. That it's both sort of something as a really good tool, but it's also something that can pose a lot of challenges. And the thing is, what's hard in microservice design is really not the microservice itself. It's all the things around them. Sort of things like discovery, coordination, security, replication, data consistency, failover, deployment, integration with other systems, etc., right? And it's also true that as soon as we sort of exit the boundary of this safe world that the microservice can sort of be, we enter sort of this wild ocean of non-determinism. The craziness that we call distributed systems, where distributed systems is really, really hard. It's where systems can fail in the most spectacular ways. When messages get dropped, reordered, garbled, and where sort of failure detection as understanding if a buddy is down is nothing but a guessing game. It's impossible to really know for sure if the one you're talking to is down forever, if it's just under a heavy load, or if we'll be back and we'll be back in a second, is doing GC, etc., or actually will never come back up. So you need to start guessing, and you need to take educated bets on who's up and not, etc. But it might sound pretty terrifying, but the good thing is it's also the world that gives us solution for all these hard problems. solutions for resilience, for elasticity, etc. Simply because a single instance can't help us much with that. You need to start introducing the network. So I really think the systems need to start exploiting reality. And one of the main benefits of microservices, it gives us a lot of good tools, sort of how to exploit reality and to build systems that really mimics how the world actually works. And that includes both its constraints and its opportunities. And there's powers in constraints. I mean, powers can be liberating. And one of these constraints is, for example, that information has latency. It's a fact that information simply cannot travel faster than the speed of light. And it often travels considerably slower. This means that communication of information has latency. And as Pat Helen says, that the contents of a message are always from the past. When it arrives to you, it always represents another another now, essentially. It always represents another sort of present, something that already happened. And in a way, we're always sort of looking into the past. It's a fact that reality is simply not consistent, not in the real world. In this monolithic world, sure, we can often assume that. To some extent, at least, if you multi-core processors, etc. I mean, sure, you can try to stop the world with locks, etc. But it's really not true, not even on a single processor nowadays. But it's definitely not true in a distributed system. Then this latency is actually very noticeable. Okay, but still, we're trying to sort of hold on to this sort of illusion of that now is absolute, that there's one single globally consistent present. And the cost of maintaining this illusion is very, very high. It can be defined as two things: contention, which is like waiting for shared resources to become available when someone's holding on to them, using them, or coherency, which is that the work that needs to be done for two sort of components or instances or something to have a common view of the world, essentially. And this affects daily life. I mean, if we think about it. It's also one way of sort of just living with the fact of reality, but it's also very true in computer science. And the first one, contention, is defined by Amdahl's law, which is the dotted line here that shows that in the effect that contention has is that it gives us diminishing returns. So in this way for you, right? So when you start adding more resources, it doesn't scale linearly, but it flattens out more and more. And after a while, it's not worth adding more resources because the contention eats up all the benefits. But the truth is actually closer to Neil Gunter's universal scalability law, which shows that when you add coherency on top of the contention, you can actually start getting diminishing returns. As when you're adding more hardware, CPUs or nodes or whatever, it actually starts to decrease in efficiency and throughput. So, and I mean, as latency gets higher, this illusion cracks more and more and more. So there's a larger difference between the present and the past in distributed systems. And once again, that's quoting Pat Helen, in a distributed system, you can know where the work is done and you can know when the work is done, but you can never know both. Okay? This is a fact. This is something that we need to embrace and work with, not against. And we need to, one way of it is like architecting systems that we try to minimize coupling and communication. Coordination, as I already said, is extremely expensive, and it's even more expensive in a distributed system because the wait times are longer and stop the world is longer, etc. And it really puts an upper bound, sort of a ceiling in what can be done in terms of scalability, elasticity, reliability, and etc. Also things like low latency and things. So, the need for coordination means that individual sort of services can't make progress individually, but has to wait. Okay, and I think it's very important that we sort of understand the words are really unnecessary. They can only do harm. That we need to start enjoying the silence, to quote Depeche Mode here. And as Bob Monkhouse says, right, silence is not only golden, it's seldom misquoted, which I just love. In a way, we need to start to learn to shut up, to avoid this chatter between the services. So cut it down to a bare minimum, at least. And it's also a fact that we have to rely on eventual consistency. Not because it's cool and because there's a lot of, all the NoSQL database vendors tells us to, but because it's a fact of life. It's how the world works, really. Once again, we shouldn't fight reality. We should embrace it, and things will actually become simpler. Not simple, but simpler, I think, to actually reach the goals and reap the benefits that we want. And once again, no one wants eventual consistency. It's a necessary evil. It's not cool. It's useful. And so two helpful tools that will help us with everything I've talked up to this point now, that I will talk a little bit in more detail about is reactive design, so embracing the reactive principles of software design, and using event-first domain-driven design. This is, I find, a great way to model the world that puts us on a path towards building systems that embrace reality. Okay, are you up for that? You don't have a choice. You can always leave, but yeah. So there's been a lot of confusion around what reactive programming is versus reactive systems. And I mean, reactive is really hyped, has been, and too much perhaps. I mean, same thing with everything that's hyped, that is like reaches peak of inflated expectations, and then it comes down to the real world. We might be there now, but I think there's a lot of good things coming out of that. It is being overloaded as well, right? Because all concepts and ideas need to evolve to stay relevant, and if people weave into more things into it, and something even better might come out. But so. Personally, I think reactive programming and reactive systems are extremely important, both of them, but at different levels in the programming model. I'll try or in system design, and I'll explain what I mean shortly. Reactive programming essentially means that, is a way of building individual services that have very good performance and utilization, etc., using things like asynchronous techniques, non-blocking, algorithms and things like that, back pressure, to make sure that you have resilience between all your stages in the component, etc. While reactive systems sort of takes a more holistic view of the world and more, full system design view of the world, and that's what we have sort of articulated in the Reactive Manifesto. However, to achieve that, you often need to rely on reactive programming. But the promise of reactive systems, building on a message-driven foundation, is resilience and elasticity. So it fits perfectly with what I'm talking about here today. So, but reactive programming, I think, is a very important technique. We need to start embracing asynchronicity more and more, I believe. And asynchronicity means different things to different people. Some think about asynchronous I/O, which means that essentially is all about not blocking threads, right? It's minimizing contention, etc. And while asynchronous communication is about not blocking requests. So it's more, which is also extremely important, of course. So asynchronous and non-blocking I/O is, as I said, is all about being as cost efficient as possible, make efficient use of the resources that you have, and giving them up when you don't use them for others to use. Okay, and contention we've already seen in this diagram of Amdahl's law is one of the things that hits you first when it comes to efficiency. And that's why I think, so the weakest link in the chain matters. So trying to make sure that your whole pipeline is asynchronous all the way is extremely important. And here things like reactive programming techniques, like reactive stream specification, these type of things Akka streams, RX Java, these type of techniques really help. But also, you know, alongside async, I think is equally important to from a reliability and resilience perspective, to embrace back pressure. I mean, it's all about flow control. So it's about that a fast producer should not overwhelm a slower consumer, essentially. And why does that matter? Yeah, I found this video on Twitter in a completely different context, but I think it really illustrates the need for back pressure very well. See, these guys, they didn't stand a chance, right, against the fish. Here's clearly that I mean, having some sort of way of telling the fish to slow down would be beneficial. Okay. So there is a need to have a sort of have a back channel. I mean, if events flow this way, you need to have a way of propagating sort of hints to say, I can't keep up. Please slow down, etc. And here's where the reactive streams specification comes in. It's a specification that was created. It was started by Lightbed, but we invited in Netflix, Pivotal, Oracle, Twitter, and others to create sort of a joint specification, because it's not worth anything if just one library does it. Everyone needs to participate all the way down up to the client that might be the one that's sort of starting off this storm of events. So if we now apply reactive programming to this macrolith, I mean, it can look something like this, right? You have this dark blue box here. It's like we sort of wrap the whole thing in reactive programming by sort of making it asynchronous, applying back pressure, streaming where appropriate, etc. Okay. I think we also need to sort of make sure that the way we communicate with the world is as asynchronous as possible, and also sort of embraces back pressure through asynchronous messaging, for example, using perhaps Kafka as a message bus or something like that, or using streaming as a way to communicate between services, not just relying on synchronous request reply. I'm not saying that all that should just be thrown out the window. Sometimes it fits the use cases very well, but it should not be the default communication paradigm between your services. So by doing that, yeah, it can look something like this. Now we're REST messaging and streaming along side by side. So I think we're getting there, but we still have a single instance of this microservice, which is by definition not scalable and not resilient. Okay. But it's equally important to understand that microservice does not come in systems, they also come as systems. And what do I mean by that? I mean that in order to build truly reliable microservices, we need to think about them as a system in itself, a distributed system. And that's what I call a microsystem. So here you have the title of the talk, right? From microliths in single instance services to microsystems. I don't know if it works. It was just something that I brainstormed up, but you get the picture, I hope. So we really need to move from microliths to microsystems. And one of the first things that we need to do here is that we need to separate the stateless behavior in the service from the stateful entity. Okay? And why is that? Yeah, it's because then we can start scaling them alongside two different axes. They have very different needs and very different sort of characteristics in how we can scale them. And by doing that, we'll look something like this, like we can split up the stateless behavior in this green box here from the stateful entity. And then we can start working with them in different ways, so to speak. Scaling stateless behavior is actually quite easy. This is what we see now with Amazon Lambda, for example. You have this whole serverless trend. It's all about that you can automatically just spin up as many instances as you need for the time being, and then just scale it down. The hard thing in all the distributed system design in general is state. So scaling stateful entities, on the other hand, we're not that lucky. It's actually a lot harder. And while I'm at it, I just have to rant about what people call stateless architectures. Like, I don't think there's no such thing really as a stateless architecture. It's just someone else's problem. You're just delegating it to someone else, which in one way might feel nice because you're not responsible anymore. But on the other hand, you know, someone else is, and now you're sitting in their lap, hoping for the best. So often I think it's better to fully embrace state as part of the system, because it really is. It's actually one of the most fundamental things in your system. And fully embrace it and take control of it and manage it in a good way instead. It's also a fact that this entity now, it actually can become an escape route from reality. I've talked a lot about embracing reality, but now we actually have an opportunity of living in this illusion, you know, that we have full ownership of time, because we have isolated our domain. I'll talk more about that. In a way that we can assume that we are the only one that is touching it, right? So that can simplify the world a lot for us. So now we can start scaling the stateless behavior and the stateful entity individually. I mean, it might be that we have a very processing and intensive system, which means that you need to run hundreds of stateless services. But we don't need anywhere close as much processing power to persist it, right? And in the simplest fashion, we probably run two instances here, like for scaling state. In some, where one is the main replica that we always talk to, while the other one is is hot standby. And often that is sufficient, but we also have the opportunity here actually to have multiple masters that takes rights, but then we have to do the work to figure all that out, the causality, etc., in between. In the end, we're actually doing some work on that now in Microsystems and logom. That we're using CRDTs. I don't know if you know about that. We can actually detect causality to do master-to-master replication of the entities. But I won't go into that here. So, but in general, reactive systems can really help us here to scale these two alongside the two different dimensions here, to really make it resilient, to make it elastic. I mean, go to a Reactive manifesto and read the basics. But in general, reactive systems are based on asynchronous message passing. Now, that is the foundation. And that gives us a way to build truly loosely coupled system that can be adaptive, where you have these autonomous components that can collaborate, where you break free from this strong coupling that you have, because everything's happening in an asynchronous fashion. And it's also the basis, the foundation for things like isolation and mobility that we'll talk about. And mobility is the foundation for elasticity. In essence, asynchronous message passing allows two things. It allows us to decouple our system in time. And decouple them in time is what gives us concurrency. It can give us concurrency on a single thread through interleaving, right? That's what Node.js and other event loop style programming models do, and that's good, right? But it also, but that's a little bit more of an event-based model. Say true message passing allows us to spread it out in space as well. So you can scale it or make it decoupling it in time and space, and it's decoupling in space that gives distribution and mobility, and ultimately also elasticity. So you can start scaling out to multiple cores or multiple machines, taking advantage of the promise of the cloud, as well as reliability. You can have more than one party that can take over if another one fails, etc. And it's all and asynchronous message passing So the essence of reactive systems is also what gives us what we call location transparency. That's quite a fascinating subject, actually, because what it allows us to do there is we have one single communication abstraction, meaning sending message from A to B, that scales across all dimensions of scale. It's the same if you communicate, within a core, between cores, between sockets, between different CPUs, between containers, between servers, between racks, between data centers, across the world. It's the same abstraction. It's the same programming model. You don't need to, sort of use, for example, threads and locks, or regular Java concurrency for working within the processors. And as soon as you want to talk across, you need to bring in message-oriented middleware or whatever, some other ESB or whatever, or raw sockets. But actually lifts the abstraction layer and unifies it all. So you have one way of working across all dimensions of scale. And the nice thing here now is that gives the runtime the ability to change the topology as the system is running. In this talk, we talk about microservices. It actually can have two services running on a single machine, just on two different cores. And they communicate with message passing, and then, the next second it has migrated over to another machine. The same communication abstraction works for the sender that actually communicates. Nothing has changed. It's now out of process, okay, but no one needs to really know. The latency, of course, will increase, but that's the really only way you should know. So it gives a lot of freedom in order to build dynamic systems that change as they are being used, which is really a must in most cloud environments today, because you have no idea, how predictable the usage patterns will be. And location transparency really is what enables mobility, dynamicity, and adaptability, and it's really what gives us, sort of, as I said, the chance of sort of moving things around. I think the Metallica quote was quite apt here. You never know where your home is, right? Wherever I lay my head is home. And it's really the path towards building truly reliable and resilient systems. It enables decentralized architecture, bulkheading for full isolation, replication, failure detection, supervision, all these things that puts us on the path to build self-healing systems. I don't have time to go into much more detail here, but it's the same thing that puts us on the path towards elasticity, also through decentralized architecture, things like epidemic gossip protocols, masterless architectures, etc., where everyone's equal and the system can adaptively grow and shrink as needed as it's being used. Location transparency is one of the keys here that puts us on the path to building truly elastic systems. And I think this is the benefit of applying and embracing sort of the reactive principles. So by doing this nice in this sort of architectural diagram, you can see we have reactive programming now inside each one of these nodes. That's this dark box. I don't have. Can I point with this? I don't know. You can see. Yeah, reactive programming is really nice for making each individual node here as efficient as possible, while reactive system sort of embraces the whole service to making the whole service as reliable throughout all these different parts, all making up this microsystem, so to speak. Okay, so how much time do I have? 16 minutes. Okay. So how can we sort of think about this and model this then? I think we need to start thinking in terms of what I call consistency boundaries, and try to sort of think, what is the consistency boundaries for a boundary for my microservice, and try to minimize the scope and minimize the part, so the data that needs to be strongly consistent. Okay. And it's really good to not start with the behavior here. Sure, you can, but in my experience, it's often better to start with the data and look for the minimal data set that you must have like full consistency in. and think about the data integrity guarantees and denormalization and all these things. And when you have that's sort of the essence, then you have the data model for your service, and then you can add behavior to that. And by minimizing this data set, you open up for more freedom when it comes to have small services that can scale more easily, minimizing coupling. And Pat Helen has a really nice framework for how to think about this, where he think about these consistency boundaries. He talked about inside data, that's our current present, that's the state in our service. Outside data, that is called blast from the past. That's that represents the past from other services entering our current now, or current present. And between services is what he calls hope for the future. There's almost something poetic about that, right? That is the commands that arrive, or sorry, the commands that we send, asking someone to do something. And hopefully they will comply and do it, but we have really no guarantees, not even that they will actually get this command and know what to do, okay? And here I think a great tool in order to model the world like this is events-first design. I think domain-driven design, most people here probably know domain-driven design, and it's a great tool, been around for quite long. But the problem with it is that most people start, thinking about the things, sort of thinking about what are the domain objects and sort of categorizing that, etc. So that gives us a way of it makes us focus on structure of things too early. Events first domain-driven design sort of teaches that we should not focus on the things, the nones, like we've been told to in classic object-oriented design as well, but on what happens in the system. What are really taking place? Who's talking to who? Who's coming? Where does things end up? How are the flows, etc. Because this is the events in the system. So I think we should really dive in to the sort of modeling through the events first, and let the events define this bounded context that can later become our service. And events represent facts. And sort of facts about the domain, facts about the world, facts what's really going on. And so the question is then, what is a fact? A fact represents something that happened in the past, something that have already happened. That is a fact. Facts are immutable. Facts don't just, come. I mean, we can't just create facts out of the blue. I mean, either facts enter our system from someone else. That's how facts can sort of accrue. Or we can derive new facts from older facts, essentially derive knowledge from older knowledge. And we're not talking about alternative facts here, just to, sorry, I couldn't help it. So what are the facts then? I mean, we should really sort of come in like a detective to crime scene and start like sort of try to mine the facts, try to distill what are the facts. And here, event storming is a technique that's been starting to become quite popular, in which you sort of bring in all the stakeholders, all the domain expert programmers in one single room. You work with Post-it notes and try to understand what's happening in the system, what are the events in the system, and then how they are related, etc. And here's very important to understand how they are causally related, because causality really starts to matter here. First A happens that causes this fact that sort of then causes B to happen, etc. So one centralized approach to do that is event logging, like we'll talk about later. A more distributed or eventually consistent approach is using CRDT's conflict-free replicated data types, vector clocks. These are often used by the tools underneath to make sense of causality. And you might ask then, okay, but what about mutable state? I mean, facts are immutable. What about mutable state? I mean, can't I work with that? I think the mutable state has its place, but it needs to be contained. It should never escape the service. You know, it's okay to work with mutable state within this sort of local sort of haven, completely non-observable to the rest of the world, doing your computation. But as soon as you're done with the computation, you should create a fact out of that and publish that to the world, so others can react on you know, and work on a stable ground, etc. You know, disk space used to be extremely expensive. And this is the reason why most SQL databases use in-place updates, destructive updates. But now disk space is incredibly cheap, and there's really no reason to not keep all history around forever. I mean, you know, all the SQL databases, they use you know, they have the transaction log and use event logging underneath, not just exposed to you. So if we as a programmers want to mine history and or before that, of course, let me sort of store history, we need to do all kinds of crazy stuff, you know, have history tables, etc., while the transaction log is actually available underneath. And I think this is wrong, right? I think that today, since the disk space is so cheap, there's no reason why we shouldn't work with the real thing, the transaction log, the event log. And I think that CRUD is really dead. There's really no reason to use update and delete anymore. We work with facts. Facts just accrue. We create facts, append facts, we read facts, and that's it. You can't change the past. So really, update is just a hoax, really. Delete as well, even though we sometimes wish that we could change the past. It's unfortunately not available to us. So we should favor event logging. And event logging is really about causality, storing the facts in the order as they arrive. Hopefully the order that they happened to. If you have multiple, you know, facts happening in different places of the system, it might be hard to actually know what the causality order is. But usually it works out. It does that in real life most of the time. And here event sourcing is a great tool. You might have heard about event sourcing. It's really about storing all events in an event log on disk as they arrive. It's a great tool for doing things, also doing things like not just storing the history, but also doing things like replay on failure. So you can just replay it up and bring the component up again. You can replay it for, you know, for auditing reasons, for debugging reasons, etc. And it fits very well with messaging and with event-based systems because you already have the events in the system already. Why not just store them and you're done? So, you know, and the log is really a database of the past, not just a database of the present, where time is the index. How time, you can really see how time progresses and how facts are laid out alongside this axis. And also event logging sort of gives us tools, you know, to avoid this infamous object-oriented relational impedance mismatch that all of us that have, you know, used Hibernate or JPA, etc., have struggled with. Because you can really have an optimal representation in memory in your objects, in your services, while they are stored in an optimal way at disk. And another pattern that is really nice alongside, it goes in concert with event logging or event sourcing, is CQRS. You know, command query responsibility segregation. And it gives us a way to sort of decouple the write side from the read side. And this is also very important. You might have like a write mostly system, so then you have the chance to scale that independently of the read side. Or if you have a read mostly system, they can have one or like two, should always have three actually. So you have but then you have like 3 nodes for writing and 30 nodes for reading, etc. And yeah, Yeah, it also, the biggest benefit, however, is probably not in the scaling and the reliability, but it gives you the chance of storing each, the read side and the write side in the optimal format for each data model. You might have if you use event sourcing, the optimal form is definitely event logging. The single writer principles, like no contention, you just write to disk, bang, 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 extremely efficient. But it's extremely hard to query that in an efficient way. So if you separate the read and the write side, then you can you use whatever query mechanism or sort of whatever data model that makes most sense for querying on the read side. It might be time series based, it might be SQL databases if you want to use, go all in on SQL, or something like Cassandra, some column database, graph databases, or whatever. So it really gives us more options for both data modeling and querying. So if we take a look at this little architectural diagram here, if we then take advantage of event sourcing and CQRS and sort of the framework that Pat Helen talked about here, then we have our client create commands here. Then our commands will enter our service. And yes, stuff will happen. We'll process them and execute our business logic. And that will sort of create a command that will sort of send down to the entity, which creates facts out of this, facts that state change has happened, and this is nothing that you then can take back. These facts then will be stored in the write model, in the event log, as they come in then, while the write model can then emit these facts to whoever. I mean, for auditing, for debugging, it might be other readers, or for replication, it might be other readers, but one reader of this can be the read model that stores it in the optimal format for reading, for querying, etc. So I think that, here we end up with a system that really has a lot of improved scalability characteristics. You can scale the stateless behavior completely independently of how you scale the persistence. And you can also scale the read side and the write side independently of each other. And it also improves resilience here. Yeah, for obvious reasons. Because you can any number of instances running here. They can take any number of instances here. I mean, and these things are usually clustered services as well. So one question that I always get is, what about transactions? And if I really need transactions, what should I do? Yeah, to quote Pat Helen again, I mean, in general, application developers simply do not implement large-scalable applications assuming distributed transaction. This is a great paper that he actually did an update for last week, this is like from 2007 or something, I think he wrote this, but he did an update last week, putting it into a little bit more context of now. But I really encourage you to read it. So what should we do then? Yeah, Grace Harper once said that it's easier to ask for forgiveness than it is to get permission. Okay? If you can't coordinate with someone and be sure about something, what do you do then? Yeah, you take an educated guess, okay, that a condition will hold, and if you're wrong, what do? Yeah, you apologize, and you perform some sort of compensating action, flowers for my wife or something like that. It usually works. So we humans use a protocol of guess, apologize, and compensate. And I really think that since this is really how the world works, I mean, other examples are overbooking flights. I mean, I fly way too much, and way too many times I've sort of come to the gate, and the flight is overbooked, and the flight attendants try to bribe themselves out of the problem by issuing vouchers, meal vouchers that are usually completely useless, or travel vouchers like if you want to travel even more with that airline. But anyway, and the same thing with ATMs. You know, they actually allow you to deduct or sort of to withdraw money, even if they can't sort of access the mainframe in the back. Taking an educated guess that you probably have coverage for that money that you want, or that you're about to that you want to withdraw. And if they were wrong when the link is established again, it will deduct your account to sometimes a negative balance, and you have to pay the interest for that. So it's really how the world works. Is once again trying to sort of embrace reality in how the world actually works, and that will simplify the world. And one pattern that sort of makes use of this, I don't have time to go through now because I have 18 seconds left, is this saga pattern, which sort of gives you a way of sort of, in short, sort of decompose your flow into discrete chunks, so transactional chunks, in which each sort of action has a reversing, compensating action. And this allows you to have asynchronous communication between each of these stages across different components. And if something wrong happens here, then we can reverse the whole transaction by just invoking the compensating action for each one of these stages. So in a way that gives you the transactionality that you want without paying the price in reduced availability, like we always do with XA transaction that never works. So there's a lot more to say, but probably overwhelmed you already. So, but in summary, don't build systems of microliths. Microservices come in systems, distributed systems, but they also come as systems. Each microservice needs to be a microsystem. And that has a lot of implications, because that means that each microservice is a distributed system. So practices that can help us here is by embracing the reactive principles, standing on solid ground, like the work of Pat Hell and Jim Gray and Joe Armstrong and Robert Virding, Erlang systems, etc. These things work. It's just that we haven't really understood how well they work yet. And also embrace event-first, domain-driven design. I think it's an excellent way of modeling your system and put you on a path towards building systems, microservices that really is not just for scaling the organization, but also take full advantage of the architectural benefits of building distributed systems. So that's all I had. Sorry, one more thing. You don't have to sort of build all this yourself, actually. There's a lot of frameworks out there that does help you. One of them that does it very much in the spirit of what I talked about is the one we have at Lightman called Logom. It's for Java and Scala if you happen to program in these languages. So that's something I encourage you to check out, because these things are hard. And we built this, from what we experience from building microservices on Akka. Our customers building Akka services on Akka and Play for the last 8 years. And so we're wrapping up the patterns and the best practices of doing so. Go to logomframework.com if you want. And I also wrote a little book about microservices architecture from a Reactive perspective. It's free. It's freely available. You can download it for free from this URL. It's very short. It's like one of these O'Reilly mini books. So that's all I had. Thank you.